So let's put together the model one by one. So an optimization problem will always have an objective function, something that needs to be maximized or minimized. You can have multiple objectives, and that takes you to an entirely new area called multi-objective optimization. We will not get there. We are just going to do single objective optimization. So we're going to have only one objective function, and the objective function can be something that you want to maximize or minimize. If you're writing a profit equation, you would want to maximize it. If you're writing a cost equation, you would want to minimize it. So here, the pollutant treatment incurs a cost. Therefore, we are going to write the cost equation on a daily basis. What is the average cost of the waste treatment on a daily basis? So that objective, that cost on a daily basis for the four cities taken together is indicated by the symbol Z. So we are going to do system-wide optimization. We are not going to optimize just for each city. We are going to optimize for the whole system, and that will tell us what each city must do in their waste treatment plants. So the cost is going to be the cost incurred by each of the four cities all added up. And this objective function Z should be minimized. So we need to minimize Z. The cost of treatment for city 1, right, is going to be P1 because that's the amount it produces. What is X1? X1 is the fraction of waste removed by the treatment plant. So P1 times X1 will be the pollutant amount treated in wastewater treatment plant 1. So if X1 is equal to 0, it means no pollutant has been treated by the wastewater treatment plant. If X1 is equal to 1, it means all the pollutant has been treated. So kindly note the meaning of Xi. It is the fraction of waste removed by the wastewater treatment plant. So this is the production. This is the fraction of waste removed by the wastewater treatment plant 1, and therefore P1 times X1 is going to be the amount of pollutant removed by wastewater treatment plant 1. So the units of P1 X1 is going to be, what is the units of P1? Milligrams per day. X1 is dimensionless without units. So there is no units for X1. What is D1? D1 is the cost of waste treatment in dollars per milligram. So for every milligram of waste that is treated, I incur a cost of DI in treatment plant I. So for treatment plant 1, this will be the cost, and D1 is going to be in dollars per milligram. So if you multiply D1 times P1 times X1, you're going to get milligrams and milligrams cancel. You're going to get dollars per day. So this is the operational cost on a daily basis for treatment plant 1 associated with city 1. Likewise, you're going to have for city 2, city 3, and city 4. So we can decide what X1, X2, X3, and X4 should be such that the treatment cost per day is minimized. Of course, we can say that X1, X2, X3, and X4 being fractions, they should be between 0 and 1, and therefore to minimize the total cost of waste treatment, we can choose X1 is equal to 0, X2 is equal to 0, X3 is equal to 0, and X4 is equal to 0. That means no wastewater treatment plants, so no cost. Well, that will minimize the cost, but the environmental regulations may be violated. That may not be the best way to reduce cost. So we have to make sure we have to look beyond this objective function because there are a few constraints. Constraints are in terms of the environmental regulations. The ministry allows only certain maximum amount of pollutant at the junctions. And then you have to obey nature's laws, which is mass balance. We cannot violate that. So we have to write the conservation equations. Now, first of all, let's look at this relationship. We already talked about this, right? The waste discharged by city 1 is going to be equal to 1 minus x1 times P1. This is the amount produced by city 1, the pollutant amount produced by city 1, and x1 is the fraction treated. So 1 minus x1 is the fraction untreated. So P1 multiplied by the fraction of pollutant untreated is the discharge amount from treatment plant 1. So W1 is equal to 1 minus x1 times P1 should make sense. And we can do it for the other cities as well. So W2 will be equal to 1 minus x2 times P2 and so on for the 4 cities. So in general, you can write Wi equals 1 minus xi times Pi. All right, so that should make sense to us. Let's now take a look at what happens in each of the junctions. Let's take a look at the mass balance in junction 1. Let's try to write a mass balance for the pollutant right here. So this stream brings in 0 pollutant, right? Because it is clean water. This stream brings in W1 milligrams per day. So what leaves this junction, assuming steady state, should be W1 milligrams per day. That should be the concentration here, right? Because the total pollutant that comes to junction 1 is 0 because it's clean water, no pollutant there, plus W1 milligrams per day. So total that comes into this junction is W1 milligrams per day of pollutant. So what should go out from junction 1 because of steady state assumption is also W1 milligrams per day. So at junction 1, what would be the concentration C1? Please note this volumetric flow rate is going to be in liters per day. So C1 is going to be equal to W1 divided by Q13. So W1 is in milligrams per day. Q13 is going to be in liters per day. So W1 by Q13 is going to be in milligrams per liters, which is the concentration units. And W1 is nothing but 1 minus x1 times P1. Therefore, I can write W1 as 1 minus x1 times P1 as already stated. So that divided by Q13 will be equal to C1. So C1 is equal to 1 minus x1 times P1 divided by Q13. So that is the mass balance at junction 1. And that is what we have here. Let's come to junction 2. Junction 2 is very much like junction 1. So you have clean water coming in here. So the amount of pollutant is 0. This stream from wastewater treatment plant 2 brings in pollutant amount W2. So here W2 is going to be in milligrams per day. The total pollutant that comes in to junction is W2. And whatever water comes in as clean water or from this discharge here, that adds up to Q23 because the overall mass is also going to be conserved, right? So this concentration, if W2 pollutant comes in to inside, what leaves should also be W2 milligrams per day. Otherwise, there will be accumulation in junction 2. So W2 milligrams per day of pollutant should leave junction 2. So the concentration here will be W2 divided by Q23. So this W2 is in again milligrams per day. This Q23 is going to be in liters per day. So W2 by Q23 will be in milligrams per liter, which is the units of concentration. So W2 is again 1 minus X2 times P2 and divided by Q23. So this is going to be C2, the concentration right here. And that is what this equation is. right? Very similar to what you see in junction 1. So you have written the concentration at C1 and C2. Now, based on what has been told to us, as the stream flows from 1 to 3, there is going to be action by natural mechanisms that reduce the amount of pollutants. So again, as the stream flows from junction 2 to junction 3, there is going to be loss of pollutant again by natural processes. So interestingly, if you take junction 3, there are going to be 3 inlet streams, one from here, one from here, and one from here. So this stream is going to bring in W3, as you can see here. So W3 is going to be in milligrams per day. This is the amount of pollutant that is discharged via this stream into junction 3. Now, from here, right, W1 milligrams per day flows. Correct? W1 milligrams per day flows from there. But what is going to happen is, because of the natural processes, by the time it reaches 3, it is not going to be W1 milligrams per day. Some of it is going to be removed by the natural action of microbes or sunlight and stuff like that. So, given that Rij is the fraction of pollution remaining as the river flows downstream from junction I to junction J. So here what happens is W1 milligrams per day starts flowing from this point. But by the time it reaches 3, you're going to have only W1 multiplied by R13 amount of pollutant, right? Because R13 is the fraction of pollution remaining as the river flows downstream from junction I to junction J. So W1R13 is the amount of pollutant that reaches this stream, right? That is going to reach junction 3 via that stream. It's not going to be W1. It's going to be W1 multiplied by R13. Similarly, from here, W2 milligrams per day flows starting at junction 2. But by the time it reaches junction 3, it will be W2 multiplied by R23 because it is from 2 to 3. So this much pollutant comes from 1 to 3. This much comes from 2 to 3. And W3 comes from wastewater treatment plant 3. So the total pollutant that comes into junction 3 is W1R13 plus W2R23 plus W3. All right. And that same amount should leave junction 3. If this is the pollutant that comes into junction 3 because of steady state assumption, the same amount should leave junction 3. So this is going to be in milligrams per day. This is going to be in milligrams per day. And if you divide by the amount of water that leaves junction 3, you're going to get this to be the concentration C3. So C3, the concentration at junction 3, is going to be the total pollutant amount in milligrams per day that reaches that junction divided by the amount of water, the volumetric amount of water that leaves that junction. Q34 is what leaves that junction 3. So this is what C3 is going to be. So C3 is going to be equal to W1R13 plus W2R23 plus W3. And we know W3 is equal to 1 minus X3 times P3. This is something we know. And what is W1? W1 is going to be equal to 1 minus X1 times P1. So W1R13 is going to be equal to 1 minus x1 times P1 times R13. Likewise, W2 R23 is going to be equal to 1 minus x2 times P2 times R23. So the concentration at junction 3 is going to be equal to this plus this plus this divided by Q34. So C3 is going to be that. Now, please note this looks somewhat different, right? So I said it is going to be equal to W1 R13 plus W2 R23 plus W3 divided by Q34. Of course, W3 is nothing but 1 minus X3 P3. So this term we are okay. This Q34 we are okay. Now, what is W1? W1, we said it is equal to 1 minus X1 times P1. That's W1. And we can write C1 as 1 minus X1 times P1 divided by Q13. So therefore, Q13 times C1 is equal to 1 minus X1 times P1. So W1 is going to be equal to Q13 times C1. Therefore, W1 R13 is also equal to Q13 C1 R13. So W1 can also be expressed as Q13 times C1 from here. Q13 times C1 is equal to 1 minus X1 times P1, which is also equal to W1. So writing it as W1 R13 or Q13 C1 R13 are the same. So this is no different from what we wrote here. So they are equivalent. It is just that we express it in different symbols, that's all. Okay, nothing wrong with either. And again, W2 R23 can be expressed as Q23C2 times R23 because W2 is nothing but 1 minus X2 times P2 and 1 minus X2 times P2 is Q23 times C2. So you can express W2 as Q23 times C2. So we get an expression for the concentration of the pollutant at junction 3. Now we can move on to junction 4. What happens at junction 4? Pollutant comes in from wastewater treatment plant 4. So you get W4 milligrams per day. So this comes in bringing pollutant into junction 4. Pollutant also comes from the stream, right, that flows here. So what comes here at this point at junction 3, just out of junction 3 is W3 plus W1 R13 plus W2 R23 if you remember. That's the amount of pollutant that comes in. And what is going to happen is as it goes from 3 to 4, there is going to be again biological action that reduces the amount of pollutant reaching 4 via this water stream Q34. So the amount of pollutant that reaches 4 junction 4 via the stream is going to be W1 R13 plus W2 R23 plus W3 times R34. That is the amount of pollutant that will survive as it reaches junction 4. Then to this you must add W4. So this is the total amount of pollutant in milligrams per day reaching junction 4. So what will be the concentration C4? C4 is going to be equal to W1 R13 R34 plus W2 R23 R34 plus W3 R34 plus W4. W4 we know is 1 minus X4 times P4. So all of these are in milligrams per day, the amount of pollutant, divided by Q45. That is going to be the concentration. So the numerator is going to be in milligrams per day and Q45 is going to be in liters per day. So if you divide, you're going to get concentrations in milligrams per liter. Now, there could be alternate ways of writing this, right? Whatever you have written here is correct, nothing wrong with it. But let's see what we have in the PowerPoint slide. So we just say it is going to be R34 times Q4C3. This is a more compact way of saying. So R34 multiplied by Q34C3. So Q34 times C3 is all the stuff. And that's exactly what we had here, right? So what we have written here is right, except that we have chosen to represent it in terms of other symbols. So this is correct as well as this is right. So we'll stick to what is there in the PowerPoint presentation, and I will let you explore other formulations in terms of other symbols, etc. Okay, so let me remove the ink from the slide. So we have all these equations. So please note, we have not done any rocket science here. All we have done is we have said what is the action of the wastewater treatment plant. So we have linked the discharges with the productions, right, using this particular equation for the 4 cities and the 4 treatment plants. Then at the 4 junctions, we have written mass balance for the pollutant. And we have expressed the outcomes in terms of concentrations C1, C2, C3 and C4. So the numerator is the quantity of pollutants in milligrams per day in each of these expressions. The numerator is the quantity of pollutant in milligrams per day. But the government and regulations are in terms of concentration, in terms of milligrams per liter. Therefore, you had to divide by the corresponding volumetric flow rates, leaving each of those junctions to get the concentrations. So that is what we have right here. And the government regulations say that C1, C2, C3 and C4 should be less than or equal to 20 milligrams per liter. It cannot exceed that. So C1 should be less than or equal to 20. C2 should be less than or equal to 20. C3 should be less than or equal to 20. C4 should be less than or equal to 20, right? The units is milligrams per liter. So these are what are called constraints on the problem. So you have to obey these constraints and still minimize your cost. That's the nice thing about optimization. That's what optimization tries to do. You're going to have a profit or a loss or a cost that you would seek to optimize. So if it is a cost, you would like to minimize it. And in order to do that, you have to obey certain principles. That means you have to obey mass balance, energy balance, etc., and other safety constraints that may exist in your system. In addition, you may have to obey some environmental regulations. For example, the mass balance gives this constraint, this equality constraint. C1 has to be equal to that. But C1 should be less than or equal to 20 is decided by the government. So what we have here is we have these 4 equations, C1, C2, C3 and C4 in terms of these symbols. So we have 4 equations right there. And we have these symbols in the problem. So if you look at our model equations here, we have these 4 equations. Please note, this is not considered as an equation because it has already been incorporated here. All right. So whenever we have W1, we have replaced it by 1 minus X1 times P1. Whenever we had W2, we replaced it by 1 minus X2 times P2. Whenever we had W3, we replaced it by 1 minus X3 times P3. And whenever we had W4, we replaced it by 1 minus X4 times P4. So this equation has already been incorporated. That's why we are saying we have only these 4 equations as written here. Then if you look at the symbols, we have symbols, if you look at it, C1, C2, C3, C4, P1, P2, P3, P4, X1, X2, X3, X4, Q13, Q23, Q34, Q45. Then R13, R34, R23. So we have these symbols. If you count, you have 19 symbols. So you have 19 symbols and you have 4 equations. The 4 equations come from mass balance, conservation of mass. So this is the situation here. So you have a gap of 15, right? 19 symbols and 4 equations. So unless you know 15 symbols, you cannot solve, right? So that's the gap that I'm talking about. What is made known to us out of these 19 symbols are P1, P2, P3, P4. So we know the amounts of pollutant produced by each city. We also know the flow rates that come out of the junctions. Coming out of junction 1 is this, the flow rate coming out of junction 2 is this, the flow rate out of junction 3 is this, the flow rate out of junction 4 is this. So we have those 4 volumetric flow rates of the river at those junctions. And we are also given the values of R13, R23 and R34, right? The fraction of pollutant remaining after the action of natural mechanisms as the river flows downstream from junction 1 to 3, from junction 2 to 3, and from junction 3 to 4. So we are given these 11 symbols. We are given values for the 11 symbols. So the point is we still have 4 degrees of freedom. That means we have 19 symbols, out of which we know 11 values. So those values are fixed. And then we have 4 equations that must be obeyed. So these are 4 independent equations that need to be obeyed. So those consume certain degrees of freedom. So you're left with 4 degrees of freedom. So you're left with 4 handles. That means you are free to choose 4 variables such that the cost is minimized. So the system provides you 4 handles. You are at liberty as a policy maker or as somebody operating the city, or you're maintaining this water body as part of an environmental agency or whatever. You have the liberty of choosing 4 variables so that you can minimize the cost. If you had no handles, you can't change the cost. But if you had some handles, you can move those handles in a certain way such that the cost is minimized. So in this particular case, we know R values, we are given the Q values, you are given the P values, and the C values are constrained by the mass balance equations. So we are at liberty to choose x1, x2, x3 and x4. So these are what are called the decision variables. Basically, they are handles that let us minimize the cost of operating this system. So the optimization problem is minimize Z by choosing x1, x2, x3 and x4. So the decision variables. These are variables that we can choose. And x1, x2, x3 and x4 should be between 0 and 1. So you can put constraints on the decision variables. But the x1, x2, x3, x4 values you come up with should give you C1, C2, C3 and C4 to be less than or equal to 20. So that would be what is called a feasible solution. That means you have to obey the constraints that the environmental agency has put. We cannot just come up with any x1, x2, x3 and x4 that minimizes the cost. x1, x2, x3, x4 all equal to 0 will minimize the cost will be 0. But if you put x1, x2, x3, x4 into these equations with the given values of P1, Q1, 3, etc., you will see that the environmental regulations are violated. So that is no way to operate a system. So you must come up with values of x1, x2, x3 and x4 that keeps C1, C2, C3 and C4 to less than or equal to 20. At the same time, it must minimize the cost for us. That's the optimization problem. Minimize the objective function by choosing the best values of x1, x2, x3 and x4 such that the concentrations C1, C2, C3 and C4 remain less than or equal to 20. We will continue this in the next presentation. Thank you.